Okay, we are going to dive in with some hardcore examples here in this last mini lecture for chapter 24. I hope this will help you really understand what you're needing to do to apply all the good stuff you've learned in chapter 24. All right, so the biggest hurdle, I think, is beginning to manage all the stuff you have added to your synthetic toolbox. So what have we added to our synthetic toolbox in chapter 24? No question that the biggest tool we've added, the most important one, is the Diels-Alder, because we're making two new carbon-carbon bonds and a cyclohexene. I mean, that's pretty good. So the Diels-Alder is the big tool, the big synthetic addition. And what you're going to do when you're thinking about making molecules is you're going to say, holy cow, that target has a cyclohexene in it. That absolutely positively means I should be thinking about some kind of Diels-Alder with this diene and this dienophile to make that cyclohexene. How's about UFDA? Yes, we've learned about syn-diol formation. So whenever I see a target that has two hydroxyl groups right next to each other and they're both syn, then that's strongly implying that that functionality came from an alkene, and I add something like permanganate or osmium tetroxide to get to my syn-diol. Finally, we've just now learned a whole bunch of new ways to make carbonyl functionality, aldehydes, ketones, and carboxylic acids. Now, that's the good news. The bad news is we tear our molecule apart in doing so, but sometimes that's to our advantage. So, for example, if I'm looking at this crazy looking dicarbonyl, well, I can imagine that that came from a cleavage reaction where I chopped that in half. So let's look at a couple of examples for that. Here's my target. Am I going to look at that and think, ozonolysis? Well, maybe not at first, but you really should think about ozonolysis as a possibility here, because it's really quite straightforward if you just think about the reverse of ozonolysis. I'm just going to put those two oxygens back together again. So I've got a 1, 2, 3, 4, 5, 6-membered ring. Aha! 6-membered ring. I'll number my carbons again. 1, 2, 3, 4, 5, 6. Carbon 1 had the carbonyl on it, so that guy is going to have to be, between carbon 1 and carbon 6 is going to have to be my double bond. Carbon 1 also had a methyl group on it. 2, 3, 4 were all CH2s. 5 had the OCH3 on it. And then 6 again is that's where we're going to cleave our target molecule. Cleave our starting material. And what we need to pay attention to here is the fact that this is a carboxylic acid. So that means in my cleavage reaction I need to use the conditions that will give me the carboxylic acid, not the aldehyde. So I have two choices. I'm either going to use KMnO4 and basic conditions and not cold. We'll just say heat. That'll take us directly to the carboxylic acid after an acidic workup to put the proton back on the carboxylate. Or I could do ozonolysis followed by our oxidative workup. And again, that's under basic conditions. So we would have to add H3O plus to go from the deprotonated carboxylic acid, because we're under basic conditions, to the protonated carboxylic acid. All right, so that is how I can envision using ozonolysis to make a target molecule that has carbonyls in it. How about this example? how would I make this pair of molecules? And that's kind of an odd question. This is less of a synthesis question and more of a puzzle question. In other words, if I carried out an ozonolysis and I got a 50-50 mixture of those two molecules, what was my starting material? Well, again, put those two carbonyls back together again. Okay, so if I move my, what is this, a 1, 2, 3, 4, 5, 6. I'll move my hexanone over here. 1, 2, 3, 4, 5, 6. And then I'll move I'll erase that oxygen and put the other piece here. This was the aldehyde. Okay, so now I'm just going to put the two together to where the oxygens end up. There is my starting material, because if I treat that with ozone, I'm going to cleave that. What am I going to need to use? Well, 1O3, but now I need to use the reducing conditions. So dimethyl sulfide or some other reducing agent. Here's a good question for you. That's not the only possible starting material for making this pair of products. What might the other one be? Okay, so let's look at a couple of examples. A roadmap will be the first one, and here it is. We're starting off by adding these two guys at 95 degrees. Well, what you should look at here is the absence of any strong electrophiles, the absence of any strong nucleophiles. That's giving you a big hint that this is probably a paracyclic reaction. Oh yeah, got a diene, got a dienophile. So those are your hints that you're talking Diels-Alder. All right, do yourself a favor, redraw your diene. Note that this is an E-alkene, so make sure you keep it an E-alkene. Make sure you think about your resonance contributor that shows the delta minus on that diene is there, and that the delta positive on your dienophile is here, and you line these guys up appropriately to make your Diels-Alder product, which looks to me like it should be this guy. And we're not going to pay any attention to stereochemistry just now. So that's the predicted product for the first step. Now we are adding, we are adding, looks to me like a very strong nucleophile slash base, and it is just regular conditions. I need to find an acidic hydrogen. Aha! I have a ketone, therefore I can make an enolate. So you need to be thinking, are these the conditions to make the kinetic enolate or the thermodynamic enolate? And these are the conditions to make, I think these are the conditions to make the thermodynamic enolate, but you know what? I think I meant to say minus 78. So we're going to go for the kinetic enolate. How's that? Just throw in minus 78. This is really cold. So that's the kinetic enolate. And, well, what's going on here? Oh, yeah. That is a carbon with a leaving group on it. Big time delta positive. I must be thinking about a substitution reaction here. So cleaning up this whole mess, whatever I am making right here has to be a nucleophile because I'm reacting it with an electrophile right there. So I say probably I'm making, if it's minus 78, I'm making this enolate, and that enolate is reacting with that good carbon electrophile to give me an SN2 reaction. And sure enough, that's what I did. So, so don't forget that this really was at minus 78. Okay, now what? Well, now focus on your functionality. You've got an alkene and you've got a ketone. It's that ketone that clued us in to the enolate chemistry in the previous step. So what's going on next? Well, I know this is a strong oxidizing agent. Ooh. And I see that it's being warmed up. I know that my pi electrons are vulnerable to oxidation. In fact, they are definitely vulnerable to being chopped in two. So I would say, under these strongly oxidizing conditions, I am making a dicarboxylic acid. So I've got a 1, 2, 3, 1, 2, 3 carbon chain, and here is my other acid. And I don't have, this isn't under basic conditions, so I shouldn't need to protonate this. So that would be my next step, and then CH3N2, well, this is the one where your Lewis structure will help you out, because once you see that diazomethane is a nice strong carbanion that can deprotonate your carboxylic acid, that means your carboxylate can very easily carry out an SN2 reaction to kick out a tremendous leaving group and make the diester. So here is our final product, CO2CH3, CO2CH3. So take-home messages here are always focus on the functionality. Think about what you're making. If you get stuck, look at what your next set of reagents are so that you can say, well, if that's a nucleophile, I must be making an electrophile, and so on and so forth. Take your cues from oxidizing agents, etc. All right, think mechanism. Example number 2, a synthesis. Okay, well, that's interesting. The things that you should notice here are, well, first off, there's a syn relationship between those two guys, and they're 1,2. If they're 1,2, you're probably thinking alkene at some point. The other thing that's pretty obvious is, oh, a cyclohexyl ring. All right, well, let's take this away. Let's make this from what? You've got to be kidding. Well, that's why I tell you we are just absolutely going to forget about the starting material. Okay, so here we go. I see this reaction, this target, and I say I'm going to make this. I don't know how to do a syn ether, but I know how to make a syn alcohol. So I'm pretty sure I could make this from this. Okay, piece of cake. I'm not even going to worry about the reagents. I'm just thinking backwards, one step at a time, to figure out what I could make this from. Okay, so what can I make that from? Well, I know how to make that. I just learned that. I know I make these syn-diols from alkenes. So that's the alkene I would want to make that syn-diol. Not going to worry about stereochemistry. That's a whole other issue. All right. So if I make that syn-diol from that alkene, I know I can do that. Okay, but how do I make that alkene? Well, there you're screaming, Diels-Alder, Diels-Alder. So I'll make that from a Diels-Alder for sure. And again, let's just do our little electron movement arrows to show. Zip, zip, zip. There's our retro Diels-Alder retrosynthetic arrows to give you this dienophile and butadiene as your diene, and we're done. No, we're not done. We don't know how to make this, but we sure know how to make that diene. We can make that from, aha! How do I reduce an alkyne down to an alkene? I know I can do it. And whenever I see an alkyne, I'm going to think, yes, I can potentially make that from this. But wait a minute, Carpenter always says you can't do that. Okay, that does not work because you can't do substitution on an sp2 hybridized carbon. So, one step at a time, I can make an alkene by dehydrating an alcohol. I can make an alcohol from the acetylide because putting on that 2-carbon chain is a piece of cake when I just react it with an epoxide. Wow. So this is a pretty hairy synthesis, and you won't see something like this for a long time. But the point is, one step at a time. One step backwards. Which reminds me of a football game. Ugh, this is a terrible joke. So, okay, so the University of Alabama football team played Harvard. So there was a party after the football game, and an Alabama player went up to a girl and said, what school do you go to? And the girl replied, Yale. And so the Alabama football player said, okay, what school do you go to? Get it? Yale. Yale. When you're from Alabama, Yale. Yale. Get it? Yale. He thought she was saying Yale, but she was really saying Yale. That was a really bad joke, really bad joke, really bad joke. Okay. See you in class.